Welcome to another coding tutorial, and in today's video, we're going to be creating a flocking simulation using a Quadtree data structure. This is the second video of a two-part series on a Quadtree data structure. So, if you have no idea what a Quadtree is or you haven't seen the first one, I recommend that you go watch that one first. But if you came from that one, let's get to work. A quick recap. A quadtree is a data structure that is commonly used to partition a two-dimensional space by recursively dividing it into four smaller quadrants. And the idea is that it allows us to efficiently manage and query or find spatial data about objects that lie in a 2D area. And in today's video, we're going to be using it to find neighboring birds within a flock of birds. Now, what is a flocking simulation? A flocking simulation is a computer model that recreates the collective behavior and movements of large groups, such as a flock of birds. It is an autonomous system, which refers to a system where each autonomous agent, in the case of a flock of birds, a bird, is capable of operating and making decisions independently of any human intervention. And when talking about flocking simulations, we need to talk about Craig Reynolds, who kicked off this whole idea in his 1986 paper, where he outlines three basic rules that an agent or a bird has to follow in order to travel in the same direction, stick close to each other, while avoiding from bumping into each other. And he describes these behaviors or steering behaviors as alignment, cohesion, and separation. He calls an agent a boid, which is shortened for bird-oid object or bird-like object. And so I'm going to also be calling these agents boids. Now fast forward to 1999, he came out with another paper, and this one is called Steering Behaviors for Autonomous Characters. This wasn't just about flocking anymore, it included other types of steering behaviors such as seek, flee, and arrival. If you're interested in learning more about steering behaviors, I recommend that you check out both of his papers as well as Daniel Schiffman's Nature of Code book, specifically Chapter 5 on autonomous agents. So in this video, the first part is that we're going to be building a flocking simulation from scratch, and then the second part, we're going to be implementing a Quadtree data structure so that we can run the flocking simulations, hopefully in a faster manner. Before we start coding, I want to lay out a few concepts and tell you about the approach that we're going to take so that it will be easier when we code. We're going to be storing a boid's movement information in a vector object. And a vector object is an object that captures both the magnitude and direction of quantities like position, velocity, and acceleration. To determine the movement of each boid, the key is to calculate a steering force. And you might have come across the equation F equals to ma, or force equals to mass times acceleration. In our case, we're going to set mass to be equals to 1, so in this case, force will be equals to acceleration. To calculate the steering force, we need to find the desired velocity. So what is the desired velocity? It is the speed and direction that we want a boid to move towards. And I want to focus on the word towards because we are not setting the boid's velocity to be equal to the desired velocity. What we are doing is finding a steering force, which is an acceleration, which is the change in velocity that will change the boid's current velocity towards the desired velocity. And this is to avoid any abrupt movement and make it look more natural. To find the steering force with two known velocity vectors, the desired velocity and the current velocity, we need to do some vector subtraction. And looking at this image, you can see that by doing the vector subtraction, we get this new vector, which is actually an acceleration that points from the current velocity vector towards the desired velocity vector. In a flocking simulation, we'll be calculating a total of 3 steering forces: alignment, cohesion, and separation. Alignment is the behavior where we want a flock of boids to travel together. So the desired velocity will be the average velocity of the boid's neighbors. And this means that the agent or the boid adjusts its speed and direction to match the collective direction of its neighbors. Cohesion is the behavior where the boids stick together. So the desired velocity is directed towards the average position or the center of mass of the boid's neighbors. And the last behavior is separation, which is a behavior where a flock of boids make sure that they do not run into each other. The desired velocity is determined by moving the agent away from its neighbors to prevent boids from crowding too closely to each other. Alright, so now that we have all of that basics down, let's start coding. I'm going to start by creating a boid class. So let's go to this arrow here, click the plus sign, and then click create file. Let's call it boid.js. And then let's reference the file. So go to index.html, copy this line of code here, and then change the name to the name of your file, in my case, boid.js. All right, let's go back to this one. We're going to start by creating a class called boid, and then inside the constructor function, as I mentioned earlier, we're going to be storing a boid's position and movement information inside a vector object, right? So these are going to be position, and I'm going to set it to a method within a vector class called createVector, which allows us to create a vector. And we're going to create it at position x and y, which are going to be the parameter we give when we, or the arguments we give when we create a boid object. Second one is velocity, which is the change in position. And instead of creating it using createVector here, I want to create a random velocity vector that allows the boid to just travel in any direction. And we can do that using a method called p5.vector.random2d. And this method here outputs a random value between -1 and 1, a random vector values. And then we're also going to set acceleration to a vector as well. And I'm actually going to set it at 0 to begin with, so we are not adding any acceleration, so there's no values for the change in velocity at the moment. Now let's draw it using the display method. How about just drawing a circle at position this.position.x, this.position.y, and I'm going to give it a size of 10. And then let's do no stroke, and how about fill it with the color black. All right, before we move forward, let's just create one boid. So I'm going to go back to my sketch.js file and then create a variable called b, and then b is going to be a new boid object. And how about we give it random values, x and y value. All right, so now we're just creating at values randomly inside the sketch, and then inside draw, we just need to do b.display. Click run. All right, so now we have a boid at a random location on the sketch. Next, let's move this boid. So we're going to create another method. I'm going to call it update. And to update the position of the boid based on its velocity and acceleration, basically we just need to add them together. So to change the position based on the velocity, which is the change in position, we just do this.position.add, and add is a method that is in the vector class that allows us to add two vectors together. So we're going to be adding this.velocity vector to this.position vector. And then let's just try sketch.js here, and then let's do b.update. Click run. All right, actually I'm going to also print out this.velocity.x and this.velocity.y so you can see how it impacts. All right, so you saw that it moves positive on the right and then negative on the y, right? So up, so negative, negative, it went in the, what is that, northwest direction. And then this one is southeast, and then this is northeast. And as you can see, it's traveling at a constant speed. And that is because the acceleration is 0. And also it's because we have not added acceleration to the velocity vector yet. So that's what we're going to do next. So to change the velocity value, we are going to do the same thing, but now we're going to add this.velocity.add. So we're adding the acceleration vector. So now by doing this, we are able to change the rate of change of the position. So we can change the velocity values. But because right now the acceleration vector is set at 0, it's basically not going to do anything. So I'm going to actually change the x value of this dot acceleration vector to 0.1. So let's see what that does. You see that? Actually, let's do it in the x direction. So it moves a little bit in whatever the initial velocity is set as, and then it moves to the right, and it speeds up. And if you look at the value of the velocity here, so if we go back to the beginning, so it starts out at negative 0.31 in the x direction, right? So it tried to move to the left, but then we're changing the rate at which the velocity changes. So as you can see here, it becomes negative 0.21, and then it just keeps going up, and that's why the position is changing to the right, but at a faster speed. Let's look at it again. All right. And that's the whole concept of how we're going to change the position of a boid, but instead of giving it a constant acceleration value, we're actually going to set the steering forces that we're going to be calculating to the acceleration here. So I'm going to set it back to 0 for now. And then what I'm going to do is that before we move to creating a bunch of boids, let's also create another method called edges. And this is basically going to have the boids loop around the canvas. So when it goes past the width, then it just comes back to inside the sketch. So we're going to write a conditional statement that says if this.position.x is greater than width, then we're going to set this.position.x to be equal to 0. Then else, if this.position.x is less than 0, then we're going to do the opposite to set it equals to width. We're going to do the same thing for the y direction. So if this.position.y is greater than height, then this.position.y is equals to 0. Else, if this.position.y is less than 0, then we're going to set it to be equals to height. All right, and then we're basically going to call this method inside update, and we can do that calling a method inside a class by just do this dot and then the name of the methods. So edges, let's try that. Save. It does it, but very slowly. Oh, all right, then it comes back. So how about we multiply this velocity vector with a certain value so that it goes a little bit faster. So let's do this.velocity.mult, which is a method that multiplies the velocity vector. And we want to multiply it by a random value. So let's do random between, how about -3 and 3. Let me just quickly make sure that it does what I want by printing this out to just check the initial velocity. All right, so as you can see here, it doesn't stay, actually it does still stay at between, no, yeah, it doesn't stay just between 1 and 1 anymore, right? Because we want it to be between -3 and 3. So there are values that is greater than, yeah, -1. Great. All right. So we can change this value within here to be greater or less as you wish. All right, so now let's go back to sketch.js, and instead of just one boid, let's create an array of boids. And then let's create another variable called num. Let's set it to, how about we start with just 10. Use a for loop to, we're going to populate the boids array by pushing what? Pushing new boids objects, right? At random width and random height. And then we need to make sure inside draw to do the exact same thing, as in creating a for loop, and then call update and display. All right, so we have a bunch of boids that just move in at different speed, different velocity, and loops around the sketch. But as you can see, they do not interact with each other in any way. They're not traveling in a flock, right? They're just traveling. Right, so how do we make them travel in a flock? So we just need to create 3 methods: alignment, cohesion, and separation. So let's do that. Right, so inside here, let's do it before update. So alignment, cohesion, and separation. So let's start with alignment, which allows us to find a steering force that will make a flock of boids travel in the same direction. So first we want to put in a parameter as boids. So we want to just figure out all the neighbors within this flock, right? The 2 key variables that we need to start with, and this will be the same for the other 2 methods. The first one, we're going to call it steering. And this is basically the steering force. And it is a vector, right? So we're going to start with just an empty vector. And we can do that by not providing any parameters inside. Next, we're going to create another variable called total, set it equals to 0. And this is how we're going to be counting the number of neighbors within this flock. Then inside here, we're going to use a for loop. And this for loop will go through the length of the boids array, right? Just to see how many neighbors are in there. And then what we want to do, the first thing is that we want to write a conditional statement that says, if what? We want to just look at the neighbors and not the boid itself, not the specific agent. We will need to check that boids of I is not equals to this, right? So just count the neighbors. And we also want to check the distance between the specific boid and the neighbors. So we don't want it to be traveling with another boid that is like way far out, right? It's not the same flock anymore. So what we want to do is that we want to calculate the distance using the dist function between the position of the boid and its neighbors. So let's start with the boid. So this.position.x, this.position.y, and then boids of I dot position dot x, and boids of I dot position dot y. And as you can see here, I used the function called dist, which is a built-in function within P5 that allows us to calculate the distance between 2 points. All right, so once we have the distance here, we're going to set distance is less than a specific radius, right? So if you are within this radius of me, basically, I'm gonna call you my neighbor. So we're gonna call this perception radius. All right, so I'm going to come up here and then set this perception radius equals to, let's say 30, right? And then now inside here, what we want to do is, now that we have a conditional statement that checks that this boids of I here is not the current void, it's the neighbor, and this neighbor is within the distance, so it's less than the perception radius. So for alignment, the desired velocity is the sum of all of the velocities, right? Of all of the neighbors' velocity. So we're gonna set steering.add boids of I dot velocity. So in this step, we're basically just adding all of the neighbors' velocity together inside the steering velocity vector. And then we're going to tally up the number of total. So now that we checked this is a neighbor, then total plus equals to 1. Next, we're going to write another conditional statement that says if total is greater than 0. So if there is more than 0 neighbor, so if there is a neighbor, what we want to do is that the 2 steps that I mentioned earlier, right? So 1, we need to find the desired velocity, and then 2, we get the steering force by finding the acceleration or the force that moves the current velocity to the desired velocity. So that's what we're going to do. First, to get the desired velocity, we basically need to divide by using div method divide the steering vector by the total number. So now we have an average velocity. And then the second one is that we need to use the vector subtraction. So steering.sub, and we're going to subtract it by the current velocity, right? So this.velocity. All right. There are 2 additional steps that I have not mentioned that we need to do in all of these. The first one is that right now we're dividing it by the total to get the average velocity, but we also want to set the magnitude of this velocity, just in case that this division results in something that's too large or too small. To make it consistent, we just set it to a specific magnitude, and we can do that by using a method called setMag, and we're going to set it to a variable max speed. And now we're also going to set a limit to the force that this steering outputs. So this is just 2 precautioned steps that we need in all of the steps to make sure that things don't move too abruptly. And we're going to do that by setting steering to calling the limit method within a vector class to set a limit, and I'm going to limit it to another variable called max force. All right, so we also need to go back to the constructor function here and then set max speed. So how about we just set it to 1 for now, and then we can play around with this value to see the impact that it has on the boids. All right, so I hope this is correct. All right, so now basically, like I said before, f equals to ma, but m equals to 1. So I'm going to just set acceleration to be equals to steering. All right. Oh, I did something wrong. So this if statement actually needs to be outside of this for loop, right? We did all of these to add all the velocity vector to the steering vector. And then after all of that is done, that's when we find this desired velocity and the steering force. All right, so I'm gonna go back to Sketch, and then we're going to come here and then just call boids of I dot alignment, and then inside here we're gonna give the boids array. Run. You can kind of see. Okay, actually, let's do 100. All right, so you can see that they aligned with each other, right? They follow the vector. So if we, let's say we decrease this to 10, you can see that the neighbors that they choose to flock together are smaller. And if I were to do 100, it's like all of them go together. All right, okay, so now that we finished with the first steering behavior, let's go to the next one, which is, how about cohesion? So we're gonna also provide boids as the argument or the parameter here. We're gonna do the same thing. We're gonna set two variables here, which is steering and total. And then it's gonna be very similar here. So first we're going to use a for loop, find the distance, and then what's different is gonna be inside here. So let's do that. So for let I equals to 0, I less than boids.length, I plus plus, and then we're gonna find the distance, right, which is this between what, the current position.x, this.position.y, and then the boids of i.position.x and boids of i.position.y, right? And then once we have this, we're gonna write a conditional statement that says if this specific boids is not equals to this, and the distance is less than perception radius, right? Then in this case for cohesion, what we want to do is that we want to find the average position of all of the neighbors, and then we're going to divide it by the total number, and that will get us the central point, or like the center of mass of all of this. And then to get the desired velocity, we basically want the current boid to travel towards that point. So inside this if statement, we need to add the position of all of the boids. So boids of I dot position, and then we just want to tally it up, right? And then now make sure to do it outside of the for loop. If total is greater than 0, then now as you can see in here, we divide it by total, and then now because it already is a velocity, we basically just subtract it with the current velocity to get the force. But here, so first let's divide steering by total first, so we get the center of mass, right, the center point of where the position of everything is, of all the neighbors is. But then we also want to get the direction from the current boid to that center of mass. So what we need to do is that we need to do some vector subtraction first. So we're going to do steering dot sub, and then we want it to be from the current position. So this basically, if you look at this image, it gives us the vector that points from the current position to the center of mass. And then after that, we want to set the magnitude to this dot max speed, the same way that we did previously. And then now we need to do some vector subtraction again to get the steering force or the acceleration from the current velocity to the desired velocity. So steering dot sub, and it will be this dot velocity. And then after that, we get the steering force basically, and we need to limit it, right? And we want to limit it by this dot max force. Okay, and now because we already set this dot acceleration to steering here, we cannot just set it to steering here. So what we're going to do is that instead we're going to return steering for both of these methods. Return steering, and then I'm going to write another method called flock, and it's gonna take in boids as a parameter as well. And basically what we're gonna do is that we're gonna be calling these three methods, alignment, cohesion, and separation, here to get the steering vector, and then we're gonna add these steering vectors with this dot acceleration. So how do we do that? So let's first create three variables, well, two right now because we only wrote two methods. So alignment will be this dot alignment of boids, and then cohesion will be this dot cohesion of boids, and then we're going to do this dot acceleration this.add, we're gonna add this force here. And then we're also going to add acceleration.add cohesion. Okay, and now this acceleration is set to the sum of alignment and cohesion. And okay, let's go to sketch.js. Instead of calling alignment, actually, you know what? I'm going to call cohesion first, just to show you how it looks. And then I'm gonna go back here, and then let's just do this.acceleration to be equals to just cohesion, right? And then let's just run. It stops. That's pretty cool. So cohesion is the behavior where the flocks stick together, and it does stick together. All right, so now we want to call the flock method, right? But first we need to also change this back to just return. All right, let's see what happens. Whoa! Some chaos. What's going on? All right, don't worry. It's okay. It is because why? So right now, if you look at this method here, we're basically adding alignment to this acceleration vector, and then we add cohesion. And then inside update, right? This acceleration, well, basically flock is being called over and over and over again. And this acceleration method is being added by this alignment vector and cohesion vector over and over again, and it never got reset. And that's why you see that it was fine at the beginning, and then it just, so the acceleration vector is at a magnitude that is like very, very large. So what we want to do is that inside update, we also want to reset the acceleration vector to 0 every time we call update, after we called all of these, right? So set it to 0, and then this acceleration method will only be with the new updated alignment and cohesion steering forces. All right, let's click run. All right, so as you can see here, they come together and they move in the direction of the whole flock. But as you can see here, we're missing the last behavior, which is separation, which gives the flock some breathing room, right? Some personal space. So let's do that. All right, so inside separation here, same logic. So start with boids as the parameter here. We're gonna start with these two variables again. And then same thing here. So for let I equals to 0, I less than boids.length, and then I plus plus, right? And then here, so let's start with, actually we don't need distance here. So for separation, it's a little bit different. Oh, no, we do. Because we need this step for all, right? Because we need to know which neighbors are counted as neighbors. So let distance equals to dist between this.position.x, this.position.y, and boids of i.position.x, and then boids of i.position.y. Now, if you are the neighbors, right, and you are within my perception radius, then now for separation, what we need is that we need to look at the neighbors, and we need to look at how close you are from me, and we need to look at the distance, basically the distance and direction at which you're traveling towards me. So we're basically is going to set a variable called neighbor vector, and this is basically a vector that points from the neighbor to me, and it has magnitude and direction, right? So we're going to set it equals to p5.vector.sub. So when we call it this way, instead of just doing the vector itself dot and then the method, it basically takes in two vectors and output a new vector. But when we do it in something like this, we basically setting this vector to a new value. All right, so but here we're basically calling this method and get a completely new vector. So we're basically subtracting two vectors, right? And the first vector is the vector that is being subtracted from, and then the second vector is a vector that is subtracted from. So look at this picture and you understand. The first one is the current position, and then the second one is the boids, the neighbor position. In this step, what we want to do is that we want to now give this neighbor vector some power, I guess. So basically, the closer you are to me, the higher the power you have. The further away you are from me, the lower the influence you have. So basically, if you're close to me, I want to travel further away. The relationship is inversely related. And we're going to do that by dividing the vector, the neighbor vector, with distance square. So the larger the distance, by multiplying it together, it gives you an even larger value, right? And you dividing by a larger value, you get a smaller output basically. So the further away from you, the smaller the influence you have on the neighbor vector. And then we want to add this value here to the steering or the desired velocity, right? So neighbor vector. And then the last step, as we have done 3 times already, we want to tally up the total number of neighbors. And then now outside of the for loop, we're going to write a conditional statement that says if total is greater than 0. Then now this is already a velocity vector because it is the magnitude and direction at which the boid itself needs to travel away. So all we need to do is first divide it by the total number, steering.div total. And then now we have the desired velocity. We want it to have a set magnitude at this.max speed. Then we need to find the steering force. So the same way we have been doing. So steering dot sub, right? We want to subtract it by this.velocity to get the steering force, and then we're going to limit it again by max force. And then we want to return this steering vector. Inside flock here, we just need to create another variable. Let's call it separation and call the separation method here with the boids as an argument. And then we're going to add it to the acceleration vector. Separation. All right, that was a lot. I hope that is correct. Let's try it. Doesn't look correct. This looks jiggly. Let's see. Or maybe it's because I set this to 100. Let's try 30. No. I think it was already correct, but maybe it was in the speed, max speed and max force that impacted it. So let's just play around with these values to see what happened with it earlier. So because the max force might be too large, yeah, so if I were to decrease this to, let's say, 0.2, let's say if I set max speed to 4, now it also travels much faster. Set it to 3. Okay. All right, so there you go. That's a flocking simulation. So what we want to do is now, only have 100, right? Let's try, let's print out the frame rate. See, around 60. Great. How about 200? All right. Start to slow down quite a bit. All right, 300. So first things first, before we implement any Quadtree data structure, the first thing that we can actually make things run faster is if you go to index.html file here, and what we want to do is, if you look at the source file here, that points to the p5.js library. Right now it points to this file p5.js, which is a non-minified version of the p5 library. And what I realized is that if I were to change this to same format as this, p5.min.js, and this is apparently the minified version of the library that compresses a lot of the unnecessary things, and it's good for performance. So if you do this, hopefully it will do what I hope it to do. Let's go back, run, and now, all right. So with 300 boids, it's still at a good 59 to 60 basically frame rate, 60 per second. All right, so let's just try, how about 500? All right, so 500 is not looking great. Let's try 800. All right, and this is where we want to apply the Quadtree data structure. So let's do that. Next, what we're going to do is we're going to go to this arrow sign, click the plus sign, and then click create file. And we're going to call this file Quadtree.js. And then we're going to reference this file inside the index.html file. So Quadtree. And basically, I'm going to copy and paste the Quadtree class that I wrote in the previous video. All right, and now let's go to sketch.js. We're going to start by creating 3 variables. The first one is Quadtree. Second one is boundary, and then the last one is capacity. I'm going to set that to, let's start with 3. So if you don't remember what these terms mean, just go and look at the other video, get some understanding, and then come back here. All right. And then inside setup, we're going to first set the boundary. And the boundary is going to be a new rect object. And the 4 parameters will be the x and y coordinates of the center of this 2D space. So width divided by 2 and height divided by 2. And then for the size, it's going to be half of the size, right? So basically this is going to be width divided by 2 and height divided by 2. So it's half, so full is going to be 400 by 400, which is the size of the canvas here. So this is the 2D space we want to set the boundary of this Quadtree. And then we're going to set the Quadtree object. Actually, we don't need let here because we already declared it outside. So Quadtree is going to be a new Quadtree object, and the 2 parameters arguments we're going to put in here is boundary, which is this, and capacity, which is 3, which is the number of points allowed in each of the square before it needs to be subdivided. And okay, and then inside this for loop here, we just do the same thing here. We created the new boid objects, right? And inside the draw function, this is what we need to do. So first, we want to clear the Quadtree every single time. So we're going to call the clear Quadtree method basically. Actually, let's click run just to make sure that everything's still kind of working. Still slow because we have not actually implemented the Quadtree structure. Next, inside this for loop here, this is where the magic happens. We're going to start by first, we're going to create point objects, right? So I'm going to actually set a variable called, let's do p. P will be a new point object, and this point object will be what? It will be this position here. So boids of I dot position dot x, boids of I dot position dot y. And then the last one, the last parameter is the boid itself, so that we know which boid that we're referring to, which point in this case. So when we have this, we want to insert all of these points inside the Quadtree. So now we have this 2D space, which is our Quadtree. Then we just insert all the points, which are the location of the boids, and we clear it so that once a boid moves, then it updates the position. What makes it very slow is that we call this flocking, this flock method on all of the boids, right? So we just look at everything as my neighbors. Well, not all the boids are my neighbors or the current boids neighbors, but we need to check whether they are the neighbors. But using the Quadtree, we basically going to just set, hey, within this range, these are the boids that we're going to check, and we want it to be actually the same distance as the perception radius that we set originally. So first, I'm going to actually, instead of setting this variable perception radius out here, we're going to set it inside sketch, same as 30 here. And then we're going to create a variable called range, and range is going to be a circular range, and it is going to be based on the x and y coordinate of the position of the boids. So boids of I dot position dot x, boids of I dot position dot y, and then the radius will be the perception radius. And once we have the range, we want to call Quadtree dot query, right? We need to find the points, and then inside query here we need range as the first argument, but actually the second argument is going to be an array of all of these points that are the neighbors. So I'm going to actually set a variable called neighbors and put it in here. And then now, instead of putting boids in here, we just put in neighbors, so the number of points should be a lot less. Save. Okay. All right, this is with 800. Let's click run. 60. Okay. All right, before we move forward, let's do a few extra things. So first, I'm going to actually draw out the Quadtree because it looks nice. Okay, and then I want to actually set the size of the boids to be smaller. Let's do it at 2. Oh, moving very fast. Okay, and how about we give it a little bit more space? Give us a little bit more room. So let's do 500 by 500. All right, and this is the moment of truth. So let's see how many we can get up to. So num is 800. Let's try 1,000. All right, still okay. Let's try 1,500. Okay, I did see some 30 appeared. So there will be some issues as you increase the number of boids, right? Because like as they travels, maybe they clump together, and then within its space, within the Quadtree space, there are just like too many boids. So you can play around, right? You can increase the number of capacity here. What if you change the perception radius, right? Let's try and do 2000 now. All right, it's slowing down, and you can see that they slow down when there's just a huge number of boids within one space. We can increase this and things change a little bit. So here is my implementation of a flocking simulations with a Quadtree data structure. So I hope that you enjoyed this series, and give it a try and let me know how many boids can you get up to. All right, see you.